Dear students and viewers, Assalamu alaikum. Here Ataur Rahman. Welcome back to my channel, Ataur's Math Edu. Now we are going to discuss an important topics: Mathematics Honors First Year, Advanced Calculus, Chapter 5, Rules Theorem. Now, what is Rules Theorem, or what do you mean by Rules Theorem? Sometime it will come in exam, state rules theorem or write down rules theorem. Now, suppose fx is a function that is the satisfy all the followings. Fx is continuous on closed interval a to b. Closed intervals write in third bracket. Fx is differentiable on open interval a to b, open interval first bracket, right? First bracket. And third case, f equal to fb. Then there is a number c such that a less equal c less equal b, and first derivative c equal 0. For better understanding of rules theorem, firstly discuss geometrical interpretation of rules theorem. The function y equal to fx is continuous in the closed interval a to b, differentiable in open interval a to b, and fa equal to fb. Now in the figure, two axes, ox vertical axis and oy horizontal axis, and draw another figure, another curve y equal to fx. In point A, draw perpendicular to a to b, draw perpendicular a from a on ox axis. In the point P, draw perpendicular from ox axis. Now here this is fa, this also fb, and also tangent, at P parallel to ox axis, and also tangent at Q parallel to ox axis. Now in the figure, fx have minimum and maximum value at P and Q respectively, in between A and B. So the tangent of the function P and Q will be parallel to x-axis. That is, the slope of the tangent will be 0. Since parallel, so tangent will be 0. So first time derivative dy by dx, or first time derivative x equal to 0 at point P and Q. Therefore, at least a value c of x can be found between a and b, where first derivative fx equal 0. Now proof. Since y equal to fx continuous in closed interval, and the function have minimum, maximum, and or minimum or both value in the interval a to b, let the maximum and minimum value of y equal to fx, capital M maximum and small m minimum respectively. Now y equal to m equal to m, capital M small m not equal to capital M. When m equal capital M, that case fx equal to constant. Small m, capital M, maximum or minimum equal, so always getting constant. We know any constant, differentiation of any constant will be 0. So first derivative equals 0. So just write first derivative c equal to 0 in between a to b. A less equal c, less equal b. Now another condition, when small m not equal m, capital M, then there exists at least a point C in between A to B, where Fc equal to M. That is, Fc is the minimum value of the function y x equal to C. Just the figure, this is the minimum value. Just h tends to 0 plus h tends to 0 minus we get less, we get always greater than. So limit h tends to 0 plus fc plus h greater equal fc, and limit h tends to 0 minus c plus h greater equal fc. This is the minimum value. Now side change fc, limit h tends to h plus c f plus h minus fx greater equal 0, and also limit fc plus h minus greater equal 0. Limit fc plus h minus fx divided by h greater equal 0. But here h tends to 0 minus, that is minus quantity. So dividing minus quantity, so here greater than change to less than or less equal. Now right hand limit f first derivative greater equal 0, right left hand limit L first derivative less equal 0. So greater equal 0, also less equal 0. So we say f first derivative equal 0 in between A to B, or A less than C less than B. Again, there exists at least a point x equal to C in the interval A to B, where fc equal to m. That is, fc is the maximum value of the function x equal to C. So in the figure, this is the maximum value. So h tends to 0 plus or 0 minus, always getting less equal, always getting less equal, since it is maximum value. So h tends to 0 plus fc plus h less equal fc. Fc always greater. Again, h tends to 0 minus c plus h less equal fc always greater than. So change this minus c plus h minus fc less equal 0, c plus h minus fc less equal 0. Now dividing h from both sides, limit h tends to 0 plus c plus h minus fc divided by h less equal 0. Again, c plus h minus fc divided by minus quantity h, that is greater less than change to greater than. So we get right hand limit first derivative less than 0, left hand limit first derivative greater than 0, greater than 0, less than 0. So we say first derivative equal 0 in between A to B. So theorem proof. Now example. Verify the rules theorem for the function fx equal to x square in the interval -1 to 1. Now solution. Given the function fx equal to x square, so f minus 1, just putting here, -1 whole square is equal 1. Now also put in 1, f1 equal to 1 square is equal 1. So left hand limit is equal right hand limit, fa equal to fb. Again another condition, fx equal to x square, just right hand limit first derivative, limit h tends to 0 plus fx plus h minus fx divided by h, x plus h whole square minus x square, just putting here. Now x square plus twice x h plus h square minus x square, just x square plus x square minus x square cancel. So limit h tends to 0 plus 2hx plus h square divided by h, just numerator denominator h cancel. So limit twice x plus h. Now putting value of 0 in, putting value of h in here, so we get twice x. Again, write a left hand limit, f tends to f first derivative x, limit h tends to 0 minus fx plus h minus fx divided by h. So x plus h whole square minus x square divided by h. 2hx plus h square divided by h. Numerator, denominator cancel h. So we get 2x plus h. Putting value of h in this in here, so we get twice x. So right hand limit is equal left hand limit for all value of x. So all condition of Rolle's theorem is satisfied. Now another one, first derivative of this twice x. Now putting value of c, putting instead of x, c is equal to c. So first derivative is equal 0, that is 2c equal to 0. So c is equal 0. So c lies minus 1 to 1. Minus 1 less than 0 less than 1. So Rolle's theorem verified. That's all. Today that's all. Thank you everyone.